I'm sorry for the very dramatic title. You don't take it too seriously. I do think deep learning is pretty cool. That's why I like to spend lots of time building deep networks and playing with them. That's what I did when I was working for the government before I joined Data Robot. So that was about 2 years ago. I was working in a computer vision lab actually, and computer vision is a very hard problem, and reading through lots of articles, lots of trying to get ideas of what we can do to improve computer vision, and I came across this thing called deep learning, and I started playing with it, and it was awesome. And then it started to suddenly show up in the news, which was very odd because most of the other things I did, such as SID features for images, they don't show up in the New York Times. The deep learning did. It started to show up, and maybe just the New Yorker just wants to copy the New York Times. So they had their own article, but then it started to show up in more and more places. I would really try to speak so you can understand me. But even lots of non-technical media outlets were reporting on deep learning, and it seemed to be kind of a big deal. Facebook and Google both made big name acquisitions involving deep learning, and so everybody wants to have some deep learning. Yahoo wants to have some deep learning. So before we get too far, let's just start with a baseline, which is this will be our definition of deep learning for the evening. It is a bunch of statistical machine learning techniques used most often to learn hierarchies of features to describe the data, and very often based on artificial neural networks. So, if you didn't know, now you know. It gets a little more hype than maybe it deserves. It's just a branch of machine learning. All we're doing. Oops. So for today, we're going to have two parts, like I said. One is going to be an introduction to deep learning, and another is going to be a survey of deep learning techniques. But I really can, how many here were here for Peter Bedenhofer's talk on creating boosted trees? Okay, we got a few. So his talk was very down to the depths in the details, had lots of code on the screen, and I wanted to do that, but it didn't seem to fit. So that's not the scope of this talk. This talk is more of a high-level talk. If you have interest in maybe a more technical discussion about deep learning and the difficulty in training them, you can just come talk to me afterwards, and we can exchange emails or whatever. That's what you're going to do. I don't want anybody to leave here disappointed. But while we're surveying people, I just kind of want to get a feel for who's in the audience. So who here has used IPython notebook? Okay. What I might expect from PyData. What about Canvas? Okay, NumPy, scikit-learn, stats models. Has anybody programmed a GPU with CUDA? Okay. Has anybody built neural network models before? Okay. Did anyone go to my talk at the Boston Data Week? Good. Good. This is the same talk. Okay, so I don't think I can stand very far away from them. So let's talk about what deep learning has done. It's done some really cool stuff. It did get published in Science, definitely laudable for them. Sure. It definitely has made a lot of headlines, and the thing that was cool for me is that it revolutionized computer vision. Computer vision was stuck for a while. They were pretty good at finding, like, if you had a picture of one exact desk from IKEA, we could find that desk in another picture, but we couldn't find the other desks. That was where we were stuck. But now, as I'll show you in examples for 10, they've come a lot further. But deep learning does not solve all the problems in the world. I'm really sorry that this text is so dark. when I did this presentation before, it was in the winter, and so none of this quite going on. So anyway, in green here, it says deep learning takes quite some time. It takes a really long time to train these models. And for how awesome and all the bells and whistles that they bring, these models are not exempt from common machine learning problems like overfitting. Still got that going on. And I think the biggest barrier is you need to have lots of practice trying to train these to do it well. There are lots of gotchas along the way, a lot of things that you can do wrong and just kind of bang your head, not really know what's going on. So they're not like solving all the problems in the world, but they do some pretty cool stuff. Deep learning does not pass Turing tests. It does not have artificial intelligence. No cure for cancer yet, no end to world hunger, and deep learning has not saved people lives. But that's not for a lack of trying. Last year there was a Gabble competition. And who has ever competed in a Gabble competition? Okay, a few, cool. I'm not Jeremy fast. So last year there was this competition that was hosted on Gabble, and basically they gave you a bunch of 2-second sound clips, and it was a classification problem. Does this 2-second sound clip have a call from the North Atlantic right vale or not? And there were sounds of like ships passing by, there were sounds of other vales. And those were all classified as negative. They had to be a specific breed of whale. Could you find it in the data? So this picture up here is of the winner. He and his team, they made a lot of entries, they did very well, and they won. And when you went on Gabble, quite often they ask you to write a blog post to say, how did you do it? What was your secret? What was the secret sauce? And he said they spent most of their time on feature generation or feature engineering. So just to make sure that we're all on the same page about what I mean when we say this. Feature engineering is the process of taking your raw data, your predictors, which we will call X, and your targets, which we will call Y. And you do something to them, some process to create another set of predictors. Like you might take differences between columns in your data set, you might spare some things, you might be much more involved things, like do a PCA, whatever, there's lots of different things. So that's what his team focused on, was this bit of feature engineering. Once that is done, once you've got a good set of features, you throw it into your learner and it pops out maybe 15 minutes later, hour later, I don't know. And for a lot of data scientists, their experience is that this part of the data science problem is what takes the most time, the most effort, and requires the most expertise. Because there are lots of really cool packages out there for doing machine learning, like scikit-learn. Once you've got your predictors and your targets, you just crunch it and it spits out a model for you. So you really need to just spend most of your time making good features. So let's take another look at the leaderboard for this data set. So there at the top is the winner. Their classification score was 0.983. An interesting thing happened on this competition, which is that there were 3 different groups that used deep learning approaches, and they all got in the top 10. There may have been more than 3, but there are 3 on the top 10. And what you can see is that they are, statistically they're tied. It's this very big difference in terms of this competition. And the other thing to notice is that whereas at the top, you can see that the winner had 70 entries, means that they created 70 different models, submitted their model, got scored, and iterated it again and again. One of these groups only had to do this 16 times instead of 70. And this is because they were able to focus on unsupervised learning. So how is deep learning different than regular, everyday data scientist doing his job or her job of engineering? Here's your slide. Contrast the two. On the left is unsupervised feature learning. On the right is just regular feature engineering. The difference is that on the left we don't include the targets. We have unlabeled data. would be if you took a bunch of pictures and you didn't have any labels in them and you put them into something to learn features, or if you had the raw text of Wikipedia and you just wanted to learn what's in Wikipedia without trying to decide is this article a fraud, is this article written in X language. You're just trying to learn things. So in the realm of unsupervised learning, the model is trying to learn what the data is, trying to understand some statistical properties that are useful in understanding the data. So in this, we said before that data scientists, that's what they spend most of their time doing. What do they do then if there's supervised feature learning? The answer is they don't do that. There's no subject expertise that goes in there. And depending on who you are, I envision there are two reactions, maybe three. First one is, I don't understand what you said, I'm sorry. That's the case, I'm sorry. One of the other reactions is, this is wonderful, the machine learns to learn. As with singularity, awesome. The other is, the scientists might say that's just BS. It's not going to work, I don't believe it. And the difference, I think, that especially where deep learning is able to do this well, is maybe not in the realm most people think about. Because most people, when they have some set of predictors, they think, like if you were trying to do, if you had some car insurance data set, and you said, okay, well, it's important to know how old somebody is, whether they're running record how, blah, 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 blah. What if, on the other hand, you have a bunch of features that they probably can help you understand the data, but you don't actually know what any individual feature tells you. The example is in computer vision. 1 pixel does not tell you anything at all. In fact, 10 pixels really don't tell you very much. But all of them together, we know they can tell us that there's something in the picture because we can do it, and we just want machines to be able to do it. So that's the trick that deep learning can do well. It learns features. So the textbook deep learning example is on this data set called MNIST. It was published by NIST, and it was basically a whole bunch of handwritten digits from the front of people's mail. And cut them. And so if you feed the MNIST data set into a neural network, and you have it properly trained and regularized, this is what visualization on the right. On the right, that's the features that it chooses to look for. In other words, it has learned that in order to look at what's on the left, it's useful to see, for example, a horizontal line or a curve or things like that. It has learned what numbers are like, which I think is pretty cool. Now I need to pause. Hammer this into your brain. I don't want to lead you astray. Deep learning is not equal to unsupervised learning because parts of deep learning are supervised. And there are many, many, many approaches of unsupervised learning that are not. So don't let me lead you astray, or don't lead you trying to tell people that I like to. So let's take a minute and talk about the fact that neural networks are pretty old. Pretty old. So why is this? Why is it exciting? Why is it in the New York Times? So let's have a little history lesson, a little story. The grandfather of neural network was this Hebbian learning back in World War II. The first usable model was the perceptron in 1957, and it was pretty simple. Basically, you would have your data, your inputs, and then you would learn some weights that you would apply to them. Multiply your weights by your inputs, you would sum them all up, and then if it was greater than some threshold, you would say, yes, this is a positive class. If it was less than the threshold, you would say no. And there was a rule that you could use to learn from your data, and so they thought it was neat, it was pretty cool. At the time, the state-of-the-art computer made by IBM had a total storage of 4.4 megabytes predicted data. So they didn't try to do very much of this. This was just like an intellectual exercise. fast forward a few years and you get to this, this book called Perceptron, in which the authors pointed out that there are some severe shortcomings in this perceptron, which is that it couldn't model any problems that were not linearly separable. So this is the XOR gate. It is not a linearly separable problem. And as simple as this is, the perceptron could never learn this. That can make people realize that there may need some additions. And at the time that they wrote this book, they already knew that. If you had a deeper perceptron, multiple layers, it could actually learn more things. And so this is the neural network. This is what is kind of stumbled into. That this is how you need to do things. Basically, you have the same idea as a perceptron. You've got your inputs, you've got some weights, and then you apply some non-linear transformation. So on these slides, when I have that little squiggle, that just means any specific non-linear transformation. So the idea was, okay, let's make this. We'll try and learn a good set of weights, and that will be a good model. And they came up with this method for training them called factor error propagation. And so they said, this is awesome. We figured it out. It's a pretty cool machine. It will learn lots of things. And then for quite a few years, it didn't learn very much. It kind of became awkward. This is probably time when everyone thought that AI was about to burst on the scene, but didn't quite get there. So the question is, why wasn't this doing anything? Why wasn't having two hidden layers any better than a single hidden layer? It should be better. It should be able to learn more complex interactions, but it just wasn't doing anything cool. And so people kind of fell out of love with neural networks and moved on. One of the theories about what was going on is that, oh, you've got this incredibly large parameter space, and it's a non-convex optimization problem. So you've probably got a little learning way somewhere, and then because you're doing a gradient-based optimization, and nobody can prove whether this is right or wrong, but it's a false idea, so they just abandoned neural networks and wrote their papers on other things. In 1995, a cousin of neural networks, this Bolton Machine. Okay. Oh my goodness. I'll change this last time. My goodness. Basically, Bolton Machine is good at classifying, separating. It doesn't have to be linearly separable, so they can use the things in perceptron. People that support Bolton machines. I read a lot of papers in revision where the idea was, I think that this is a cool feature to apply to images, so let me generate these features and then feed it into the Bolton machine. Here are my results. Publish on the page. So in between then and now, what happened? How do we get to here from people who support Bolton machines and neural networks not being very popular now? In 2006, there was three actually versions that were going on at the same time. These three are Jeff Hinton at the University of Toronto, Joshua Benjo at the University of Montreal, and John Hood. They all, in 2006, came up with a way to get deep neural networks easily to train on. And as a side note, they have been rewarded for their breakthroughs. Jan Hood is now the director of research in artificial intelligence at Facebook, and Jeff Hinton, they hired him on Google. I think they just wanted to snatch it off so nobody else could get it. I don't know why I always tried to hire Joshua Benjo for him, but so back to this problem. Why wasn't this working? The common theme, those three, they're separate, figuring out what was wrong with neural networks. They all kind of settled on the idea that you set your weights randomly initially, and then you're trying to follow some gradient down to where the best weights are. And because of the nature of factor error propagation, you would never learn a good set of features. from the beginning. So you're essentially doing a random transformation of your data and trying to explain it from there. So that's why it wasn't doing so well. There's another answer to why neural networks are new, and it has something to do with this guy. Does anyone know who this guy is? This is Gordon Moore. Moore's law. We have much faster computers than before, especially GPUs. GPUs have helped a lot in just doing the raw number of calculations that we need to get neural networks to work. Because essentially, at the end of the day, you're doing lots of matrix computations, followed by unary operations, those dominating transform. So let's pause. What is it doing to deep learning? What's the difference between regular neural networks and deep learning? And this is the answer according to what we're going to do. This is a shallow neural network. This is a deep one. This is a shallow one. Deep equals 2 plus 2 or more is deep, 1 is shallow. That's the definition. And it's not really any more complicated than that. So if people get all excited about deep learning, you can just know in your head, they just need to do it. So what do these separate layers play? Before when we were showing the zip codes example, that was a single blood. So if you were to feed in a bunch of faces into a properly architected neural network, what would it choose to look at? What would it choose to think is important? You learn these features. So at the very lowest level, it thinks that it's important to look at local contrast, tracing an edge, seeing where the physical intensities are high or low. Those are the things that it thinks. Then the next thing that is important. Sorry, Jeremy. Thank you. The next thing that it thinks is important are these parts of the face. So your eyes and your nose, those are pretty useful in understanding somebody's face. And then at the top, just actual face templates. So you can imagine that if you have built this neural network that is able to match face templates, then that would be pretty useful if you were trying to build, let's say, a gender classifier. Like that guy with the mustache, probably not female. These sorts of features are the things that we dreamt about in computer vision because this is a pretty broken problem. So anyway, that is the introduction to deep learning. We're going to break now. We'll have time for questions at the end. We're going to break now. So that was our introduction to deep learning. Maybe it was too high level. Maybe you guys want more details. I'm sorry. If you want more details, let me know. I always like to talk. I will always take the spotlight. So if you want me to talk about that, I can do that. Now what we're going to do is we're going to talk about a survey of deep learning techniques. Deep learning is covers a lot. Deep learning is very much an umbrella term, hence my umbrella. So this is going to be like a zoom by discussion of these. It will be wholly unsatisfying if you're interested about hearing any of these individually. But it's just to give, this is like if I were to go back in time to down 2 years ago when I said these are the things you need to learn, I would do this. So what we talked about before, some people pointed out that I didn't make the relationship clear. Jeff and Yoshua Benjo and Alan Kuhn, they were doing unsupervised feature learning to initialize the weights in the first layer of their neural network. That was the trick. And so these are the kind of buzzwords you need to know about in unsupervised feature learning. The first is an autoencoder, and if you're not familiar with an autoencoder, it is just a neural network that you feed data in, and you want to get the exact same data out. That's all it is. And it sounds pretty pointless and a waste of time. What you're trying to do is, like, you're trying to go from your original feature space down to a smaller feature space. That's one thing you can do, is in effect, you learn a dimensionality reduction. Another thing that you can do is with proper regularization, you can project yourself up into a much higher dimensionality, which sounds silly, but you can do it in such a way that you learn a sparse over complete representation of your data, which has its own wonderful benefits. So this is one of the ways that you can initialize the weights to your neural network. And we're not going to talk about all of these, like I said. The next one we're going to jump into is the restricted Boltzmann Machine. This is Mr. Boltzmann. I love that beard and those fierce eyes. I think that he would do very well if he were alive in Boston these days. Boltzmann's name is normally associated with thermodynamics because of the way that his theory about how particles interact gives rise to temperature. And it seems very strange that his name should show up in feature learning. But basically, what they've done is they created a model where if you were to directly translate it, it would be these particles at the bottom don't interact with each other. They only interact with the particles at the top. And then what would that model be like? And then if you stare at it hard enough, you can think, okay, those nodes down at the bottom, that's my input space, and then up at the top, that's my features. It sounds a little simplistic, but that's what it is. You learn some weights, just like in thermodynamics, you learn these weights that determine your system. In machine learning, we learn these weights, then we transfer them into our neural network, and magic ensues. Our neural network does better. So that's our brief introduction to the unsupervised methods in deep learning. There are different kinds of connectivities inside your network that are useful in different situations. The first is a traditional neural network. This is what I was talking about before. You have like stepwise, you have your inputs, they all get fed through to the next layer, then also get fed through, and so on and so forth, so we get a useful output. One thing, locally receptive and convolutional neural networks, those are very much invented for computer vision. The idea is you don't need to learn a weight for every single feature from your input space to your projected space. Really, this is a shortcut for computation. This is just so you can cut down on the size of your matrix that you're multiplying by. But it can be useful if you have lots of data. I don't know if it's clear, especially since it's somewhere, but essentially those top three inputs go to that first output, but not to any of the others. And the last one is a recurrent neural network. So instead of going from input to the next layer to the next layer, there are actually connections from the layer back to itself. So in this way, the neural network can keep state, can remember what it has seen before. And so these kinds of neural networks are useful for time series data. Also useful for natural language processing. When you've got a stream of words going through, you kind of would like to remember what came before. This is probably the most important. I'm going to spend the least time on it, but there are lots of training tricks for neural networks. One is that stochastic gradient descent is a first order optimization problem, but if you spend lots of time playing with differential equations, you know that you can do higher order approximations. One of the problems with neural networks is that they just have such a high dimensionality that computing that second order information is very costly. But this is what I got some questions about during the break was which activation function should I use? I'm very sorry about these slides,
But over there on the left is logistic sigmoid, in the middle is the tanh function, on the right is the rectified linear unit. The short answer for which one you should use is this one on the right, the rectified linear. Just take my word for it. It's actually, it learns slower, but it is in practice much better results, according to Defected, if you believe him, which I do. And then data processing, this is probably the most important thing because neural networks are very fragile things. When you think of a neural network, you should think of a porcelain doll that is standing over the edge of a cliff waiting to break, because it will. Neural networks like data that is normally distributed or binary. Those two are very nice. Anything that is a heavy tail distribution is just going to break your neural network, I promise you. So you have to do some sort of treatment of your data, whether it's subtractive mean and divided standard deviation, so that's worse for heavy tails, or converting it to percentiles of your column is really useful. But you have to be very careful, because if you put the wrong data in, or if you target the wrong data, with I don't need to target the wrong data, but if you put in data that's hard to model with a neural network, it will break. And then there are different kinds of regularization, and I wanted to spend more time talking about this, but it just didn't quite fit into the flow of the talk. But I can talk about this then you do through an email or afterwards if you want. But when neural networks started, they said, let's throw an L1 penalty or an L2 penalty on the weights. And what that ends up doing is that you spend all this time learning a really good feature, which is these weights, and then you shrink your weights back down towards zero, and you essentially throw away what you have learned. So this is not recommended. Noise injection is very good for helping you to artificially increase your data set size, which in some domains can be a problem if you don't have enough data, but you're trying to learn 40,000 parameters. That can be problematic. But let me just jump forward down to this dropout business. This is the recipe that Jeff Hinton will put in his cookbook for neural networks for now. He gave a talk at NIPS in December, and this is his thing. So it's a deep rectified dropout network. So deep is greater than 2. We talked about before. A rectified linear unit just means that if what goes into the unit is less than 0, it's 0. Otherwise, it's just the value. And then dropout is this technique of randomly dropping half of the inputs of any layer. And what this does is it helps you to prevent co-adaptation of features. So let's say that in your input set you had 2 features that were very correlated but very important. Often in most machine learning domains, what ends up happening is that one of them gets learned as important, the other one just gets thrown away as not as important. And this helps you avoid that situation. So this is the umbrella of deep learning. It has grown since the last time I gave this talk. But basically, what you do is you shop around, find some techniques, and then you find your data, and you play, and you write a paper. That's what you can do. So, okay. So there are 3 applications that I want to go through of where deep learning has done some pretty cool stuff. First is in the speech domain. So these are examples from this guy, Rob H. This is his own private hobby website, and he just likes to look at these waveforms of speech. And he has this whole website describing how you can look at it. But I just make this picture from him. But anyway, you can see here that when you say the word ball, it looks different than when you say the word bar. And see the bar go down. Yeah, it's a popular time for phone calls. So anyway, if this is the data you're looking at, if you're looking at speech data, You want to see, okay, what will a neural network look at? So this paper specifically used a traditional full connectivity in pre-trained using an autoencoder with L1 penalty and rectified linear units. And this dropped out. And most of you are probably saying, ooh, cool, well, tell us what you're looking at. Okay. So these are the features down at the bottom. This is kind of like when we're looking at the zip code numbers. This is what the neural network likes to look at when it's looking at waveforms. And so to help make it more clear, the authors of the paper pointed out these examples. So on the left is a filter that the neural network learned that it thought was important. And on the right, they just kind of fished through until they found what it was. So it learns to look for the sound A, and and R, and a hard T stop. So this T stop, it kind of looks fuzzy, but you can see where it goes from white, which is high intensity, to black, which is low intensity. So that's where all of a sudden the speed stopped. So this is a really cool result. They had a pretty impressive gain in performance over state of the art. And this is my favorite. There's this competition called ImageNet. They've had several editions of this competition, but basically they have a very, very large labeled data set of images. There are over 10 million images and over 10,000 discrete labels that they attach. So, this picture on the top left is a picture of a lens cap. And you might think, well, that's a picture of a camera, but you'd be wrong, because that's what the label says. But that's just the shorthand. This is the game that they play. There's one label associated with an image. Can you build a machine learning system that will predict the right label given the data? So in 2012, one of Jeff Hinton's students built a neural network that had convolutional layers and actually got a really complicated setup with rectified linear units, and he used dropout. And so what happened? This is the result. And so right under the picture is the correct label. So this picture of a pint up in the top left is indeed a pint. And then down below, there are 5 guesses. Those are the top 5 guesses from the neural network. And the pink and blue is just like a representation of how confident the system is in what it is. So that container ship is very, very, very confident that it's a container ship. But one that's maybe less interesting is this picture down at the bottom. This picture is definitely a picture of a cherry, and this is not a picture of a Dalmatian. So anyway, the point is that this system does very, very well, and the errors that it makes are errors that are kind of understandable. In other words, computer vision made like huge leaps and bounds in what they're able to do. And it's probably the reason why Facebook will be able to tag you in your friend's pictures by itself. Sorry. The next really cool example that I like is in natural language processing. So they have this data set that has a bunch of transcripts of the news in different languages. So at the top we have English, down below we have Spanish, and below that, does anybody know what that is?
Turkish.
Czech. I think that sounds Turkish, better than I would. So anyway, if you tokenize your words as however you want to do it, and then you feed this through a recurrent neural network using both logistic and softmax units to learn mapping from language to language. This is the kind of automatic translation that it does. So if you feed it the word pets, it thinks that the word that is most similar to pets in the Spanish language is mascotas. And on the right, you see. So in other words, we've learned automatically a translation from English to Spanish. Now there are some words that it did not get correct. First one is that prayers, the word is not oraciones, but the word is rezo. But I speak Spanish, I can vouch that those are synonyms. Campo corto or short stop, also synonym. Muy and ultra, also synonyms. So it's not perfect, but isolated words, it's very easy to pick out examples where you got it completely right. When you do sentences, it's less so. But it's very impressive to me that this deep learning approach can give you huge gains in speech recognition and in computer vision and in natural language processing. So you take all these together and you have to say, are you telling me now that in the future there will be robots? Probably, I don't know. There's probably going to be robots. Google's spent a lot of money on robots lately. I don't know how far deep learning will come, or if they'll throw that way and pick whatever gives them the next results. But I can tell you, I think that it shouldn't be too hard to come up with some pretty cool examples of how to use deep learning. This is, I don't remember the technical term for this, but EKG, thank you. So the one on the bottom is atrial fibrillation, and generally you have to go to a doctor to help you diagnose that you have atrial fibrillation. But what if you lived in India and it was like an entire weekend trip to go see a doctor? Would it be cool if you had an app that could listen to your heart and tell you if you had some sort of heart murmur that you should go check out? This is the kind of thing that it seems to me should be looking at improving. Because we can recognize speech, we should be able to recognize what the heart is saying. Another, I think that Google is obviously trying to get cars to drive by themselves. So it would be awesome if the cars could see the roads, but it would also be awesome if the roads could see the cars and automatically control green lights and red lights to kind of guide the flow of traffic, cut down awfulness like this, type spice traffic. And the third is, this is also from Star Trek. I didn't realize before there were 2 Star Trek references in this talk, but there it is. This is a universal translator. There was a really impressive demo by the director of research at Microsoft that he gave while visiting Microsoft in, I don't know where exactly in China, but it was in China. Anyway, during the course of the talk, he explained what it had been using deep learning for. The first trick was to automatically transcribe what he was saying, which was cool. Then they automatically transcribed what he was saying into written Chinese, which was also pretty cool. And then the last trick that they did was that they translated what he said into English, back to Chinese, and then spoke it in Chinese. So he spoke, and then a few seconds later, the system spat out what he was trying to say in Chinese. And it was probably flawed, but I think that it's really impressive that this technology that we thought was so awesome, we put it in sci-fi not too long ago, is coming close to home. So deep learning, no, it's not true artificial intelligence. It hasn't passed the Turing test, and it hasn't cured cancer, but it might. There's some interesting things to talk about. There was a Kaggle competition 2-ish years ago that basically Merck sponsored, and they had a whole bunch of data that was trying to predict biological responses to different chemical compounds. And I think that they tried to make it as obtuse as possible, so you couldn't actually apply any biological or chemical or chemistry knowledge. And the winners of this competition was not a robot, but Jeff Hinton's group. They used deep learning to actually learn some useful representation of how chemical compounds interact with the cell, and they were able to win this competition. So there is a lot of promise. Yes, it's cool to see examples and progress in computer vision and natural language processing and speech recognition, but I think that there are there's a lot of opportunity to do good in realms where data science hasn't seen as much success before. So this is the whole view of deep learning. That's it. You know it. You know deep learning. Congratulations. I tried to imagine if I came to this, I would probably want to leave knowing what I should do next, where I can go to get some more. Let's see how this is a PyData, or not PyData, that's the thing. Something else. This is a PyData Meetup. This is very Python focused. So these are all GitHub things. I like to pull packages from GitHub because I think it's quick and it's awesome. These first two are actually both students from Jenkins and Flood. And I don't know why they don't share work, but it doesn't seem to be what they do. But those are really good starting point if you want to just kind of jump right in and try and get going as fast as you can and learn some stuff about deep learning. This next one I learned too is by the group in University of Montreal. And it is much more actively developed. There are pushes to the code base every week. The other two, since it's one single grad student, not so much, but they're very cool. But if you like didn't bring your cell phone to snap a picture, or you didn't bring a pen to write it down, if you just go to deeplearning.net, like you can think back with it. What was that kid from Data Robot talking about? Deep learning and .net. Don't go to .com. I don't even know what's there. If you go there, there are links that point you to these, and so you can start to play with what you want. So let me, I guess, wrap it up real quick. So the title, very self-aggrandizing title, the future of machine learning and artificial intelligence. I don't know if deep learning is really the future of artificial intelligence and machine learning, but I know that it is present. I know that there are a lot of gains that we're going to be seeing, and I know that there's been a lot of investment because of the promise that some of these big players see. So anyway, my name is Alan Kagi. Thanks for coming to the talk.
Thanks for the talk. It's very interesting, very presented. And can you say what are the biggest decision points when you are constructing an artificial neural network with deep learning for you? Usually, what are the biggest decision points?
That's a hard question. One of the things you find when you start playing with neural networks is that there are many decisions to be made about the learning rate, your hyperparameters, your architecture, how many layers, how many nodes in the layer. And unfortunately, they're all confoundingly interrelated. I think I wish I had some good rules. I know that there's some papers that are trying to formulate some good rules, and I don't think I had that much success. Me personally, I try something, I run with it, and I'm convinced that it's not right, and then I keep going, which isn't very satisfying. But unless you like to play with deep learning, which I do, very satisfying. Sorry, don't really have any that are kind of close. Any other questions? Sure.
Can you give a sense of what's the largest amount of data that you try to train on and how long it took?
I guess I will tell you from Google, they did a result from they took 200 million pictures from YouTube. They fed it through a neural network, and they had an incredible, they built their own message passing system with GPUs. No, not GPUs, excuse me. That took them 2 weeks to train. Then Andrew Ng from Stanford, he did exactly the same thing, but instead of having it on a huge cluster, he just did it with a bunch of GPUs, and he did it in a day. So that's the kind of range. If you've got 200 billion inputs that are 256 by 256, that's kind of how long it can take. It definitely, your mileage may vary, especially if you don't have top-notch engineers to communicate the interconnects between your machines. Sure.
Where would you classify hidden Markov models in this taxonomy of techniques?
Hidden Markov models I know have been used kind of in tandem with deep learning, but I don't think they quite fit exactly in the same taxonomy. So, hopefully that's yeah.
So this metaphor of building superstructures from smaller structures, which is applied to deep learning, is applied in other areas like genetic algorithms, various other models. Do you see it also what's the same advantages in SVMs and other models?
I know that one of the approaches, MNIST, the zip codes problem that I was talking about before, that's kind of been the benchmark that people talk about. And one of the approaches that somebody did was that they built a big set of features and they just concatenated the output of every feature and fed that straight into an SVM, and that actually did really well. So it's not necessarily that you have to use your neural network for your decision function. You can actually just use it for features. They get fed into a separate model.
So, I mean, when I look at the number from the last Kaggle competition, I think they've gotten the top one 49.494, and the next one is 0.486. So I'm trying to understand why this is considered a revolution. If you're going from like 48.6 to 49.4, is in vision, are they getting much bigger gains than you're seeing in other places, or?
So I think that in that competition, that might not be the best way to see the gains.
Yeah.
What you can see is huge breakthroughs in computer vision. The task of saying assigning a single label to an image, the other groups perform. It was just like leaps and bounds ahead, and so that's kind of why you hear more about those applications of deep learning, is because there really was no other approach that was coming close.
Sorry, so now that we can hear you better, can you say again, what is it about double encoders and RBMs that caused neural networks to be popular again?
Yes. Okay. So the whole point of autoencoders and restricted Boltzmann machines being used to make neural networks popular was from the way that the backwards error propagation algorithm works for training neural networks. The learning signal that you get for the first layer, it was very, very small. So you would start with a randomly set weight in that first set of features, and then you were hoping that you would get to learn something. But since the actual value that got back propagated down to that layer was so small, you never learned anything. And so you essentially started with a random projection, and then where you tried to learn it as best you could from that random projection of data. So now that you can learn some features that are useful, you use that as your first layer. You initialize the weights. And that was, they just made a breakthrough because they weren't doing random projection anymore. Okay, so I'll be around if you want to ask any more questions. I think I should definitely mix and mingle. Thank you very much.